focus of this lesson is on an introduction to solving absolute value inequalities. So the absolute value of x is less than 3 means the distance x is from 0 is less than 3 units away, or within 3 units. And so if you think about where x would be, we're saying that x could be anything less than 3 units away. So if we were at 3 units away, that would put our x's at -3, and that would put our x at +3. But it turns out we can't actually hit -3, and we can't actually hit +3, but we can approach -3 and approach +3. And so if we're less than 3 units away, we could be -1 unit away, we could be -2 units away, we could be -2.9999999 units away. But the point is, on the negative side, that would be this shading. And then on the positive side, if we're less than 3 units away, we could be 2 units away, we could be 1 unit away, we could be 2.999 units away. We could be anything away that's less than 3 units, and that would be this shading. So at the end of the day, this is actually a representation of two inequalities. Our x could be bigger than -3, but not anything bigger. We'd also have to have the condition that x is less than 3, so it'd have to be both things. So it'd be the intersection of x is greater than -3 and x is less than +3. So continuing with that idea, let's take a look at the example, the absolute value of x minus 5 is greater than 7. This means the distance x minus 5 is from 0 is greater than 7 units or beyond 7 units away. So if we were at 7 units, that would put our x minus 5 at -7, and that would put our x minus 5 at +7. But we're saying we're more than that, so we're more than 7 units away from 0. So we wouldn't actually hit that -7, and we wouldn't actually hit that 7, but we'd be further away from 0. So further away would be to the left of -7, and further away would be to the right of +7. And that would represent our solution at the end of the day. But then what that means is x minus 5 is less than -7, because to the left of -7 means less than -7. And it would also mean, or well, it would be x minus 5 is greater than 7, because that represents to the right of 7. So it's an or statement here. We are not looking for the intersection of these two solutions, we're looking for either or. Either or would have to be true. And so our absolute value of x minus 5 is greater than 7 splits into x minus 5 is less than -7 or x minus 5 is greater than 7. Our last of the three examples is the absolute value of 7x is greater than or equal to 9, which just means the distance 7x is from 0 is could be equal to 9, or it's greater than 9 or beyond 9 units. So I'm going to go ahead and look to the left of 0. 9 units away would be at -9, and 9 units to the right of 0 would put our 7x at 9. And we're saying we could be equal to those values, so we could be having 7x equal to -9, but we could be also greater than that -9. So equal would put a bracket at -9, but greater than that distance would put us to the left, or beyond that distance would put us to the left. So this would be 7x is less than or equal to that -9, or we could have 7x being greater than or equal to 9 units away. So that'd put a bracket at 9. And if we're going to be beyond that, we're going to be to the right. So that means our 7x could be greater than or equal to 9. So our absolute value splits into two inequalities. The first is exactly what you see, and then the second is exactly what you see but do opposite of the side that doesn't include the absolute value expression, but then the symbol also has to flip. Now let's go ahead and consider our four possibilities for absolute value inequalities. And so this is assuming that a is a positive value and x is an algebraic expression. Then if we had the absolute value of x and we had any of these four inequalities, then they are different in certain ways. So the first, the absolute value of x is less than a units. You're saying you're within a units, and so that means your x is within the interval negative a to a. It's bigger than negative a, but it's also less than a. So it's an and statement, it's an intersection of those two ideas, and you can think within for less than. If you have the absolute value is less than or equal to a, the only difference is you could equal a, and so that puts brackets on your interval. So you could have x being in between negative a and a. If you have absolute value of x is greater than a, you're saying that your distance is beyond those a units away, and so you could be x could be bigger than a, or x could be less than the opposite, the negative a. And so that's two different intervals being unioned together. So negative infinity to negative a, union a to infinity. So that's your distances beyond, kind of like the examples we just showed. And then the same thing for the absolute value of x is greater than or equal to a. The only difference in that case would be that your x could be equal to that a value. So it could be equal to the negative a and it could be equal to the a, hence the brackets. But those are your four different scenarios. Now, as far as the procedure for solving absolute value inequalities, it's very similar to the procedure for solving absolute value equations. You need to isolate the absolute value expression first. So if there's any operations going on outside of the absolute value on the same side of the inequality, you'd have to undo those first. But then once you did, you'd split your inequality into two inequalities. The first is exactly what you see without absolute value symbols, and the second is where you multiply by a negative on the side without the absolute value expression. And when you do that, you also need to flip this inequality symbol. And then in both cases, you'll solve for x. You want to draw it, and then you would write your interval notation, and then you would check your solution at the end of the day.